Welcome to Mindcast, the podcast that explores the fascinating intersection of artificial intelligence and cognitive science. I'm your host, Will, and each week we dive deep into the stories behind the technologies that are reshaping how we think about thinking itself. Today's episode is going to blow your mind. We're uncovering one of the biggest misconceptions in modern technology, the myth that today's conversational AI evolved from those clunky chatbots of the 2010s. The real story is far more surprising and reveals something profound about how revolutionary breakthroughs actually happen. We'll journey through two parallel worlds, the commercial chatbot industry grinding away at rule-based systems and academic researchers quietly developing something that would change everything. By the end of this episode, you'll understand why the AI revolution came from a place no one in the commercial world was looking, and what that teaches us about innovation itself. So buckle up. This is the untold story of how conversational AI really happened.
You've probably heard that today's powerful AI systems like ChatGPT evolved from those clunky 2010s chatbots. But here's the truth. That's completely wrong. The conversational AI revolution didn't come from improving old chatbots. It came from an entirely different academic research breakthrough that blindsided the commercial world. This is one of the most fascinating stories in modern technology, a tale of two completely separate worlds working on the same problem with radically different approaches. It's like watching two groups of explorers trying to reach the same mountain peak, one group slowly building a winding road up the mountainside, while another group discovers they can fly. The road builders never saw the pilots coming. Today, I'm going to take you on a journey through this unexpected story. We'll explore how the commercial world was trapped in a dead-end approach for over a decade, while academic researchers were quietly developing something revolutionary. By the end, you'll understand why the AI breakthrough that changed everything came from a place no one in the chatbot industry was looking, and why this story reveals something profound about how innovation really works. To understand this story, we need to first paint a picture of the technological landscape in 2010. This was a pivotal moment in digital history, a perfect storm of technological conditions that created an unprecedented demand for conversational AI. Let's set the scene. Internet penetration had reached a tipping point, with over 2 billion people now online globally. Smartphones were exploding onto the scene. The iPhone was just 3 years old, and Android was gaining momentum fast. Social media platforms like Facebook and Twitter weren't just connecting people anymore. They were becoming primary channels for customer service interactions. Think about what this meant for businesses. Suddenly, customers had 24/7 access to complain, ask questions, and demand support across multiple digital channels. The old model of customer service, call centers with set hours, was completely inadequate. Companies were drowning in digital customer interactions they couldn't possibly staff for. This created a massive market opportunity. Businesses desperately needed a way to automate customer interactions at scale. Entered the enterprise chatbot industry, which promised to solve this problem with sophisticated conversational AI.
Let's dive deep into what these enterprise chatbots actually were. The poster child of this era was British Telecom's virtual assistant, Aimee, launched in 2010. Aimee was considered state-of-the-art, and her architecture reveals everything about how the industry was thinking about conversational AI. Aimee was built on what we call a rule-based decision tree system. Picture this like a massive flowchart. If a customer says X, respond with Y, then ask Z. If they respond A to Z, go to branch 1. If they respond B, go to branch 2, and so on, branching out into thousands of possible conversation paths. The system relied heavily on keyword matching. Engineers would manually program responses for specific words and phrases. If a customer typed bill or payment or charge, the system would route them to billing-related responses. If they said internet or connection or slow, it would route to technical support. This approach required an army of conversation designers, linguists, and programmers to manually map out every conceivable customer interaction. British Telecom employed dozens of people just to maintain Aimee's conversation trees. But here's what's crucial to understand. The industry knew these systems were fundamentally limited. They had what they called a designed for failure philosophy. The goal wasn't to create truly intelligent conversation. It was to handle the most common, routine queries and then gracefully hand off complex issues to human agents. Success was measured by automation rates. What percentage of customer interactions could be handled without human intervention? A good enterprise chatbot might successfully automate 60 to 70% of simple queries. The remaining 30 to 40% were expected to escalate to humans. This wasn't seen as a limitation, it was the intended design. While enterprise chatbots were trying to automate customer service, another branch of the commercial world was working on voice assistants. Amazon's Alexa, launched in 2014, represented a completely different approach to conversational AI, but one that was equally trapped by the same fundamental limitations. Let me walk you through Alexa's architecture, because it's genuinely impressive in its complexity, even if it was ultimately a technological dead end. When you say, "Alexa, what's the weather?" here's what happens. First, wake word detection, using a local neural network. Then, automatic speech recognition converts your speech to text. Next, natural language understanding figures out your intent and extracts key information. The system then dispatches your request to the appropriate skill, essentially a mini application. Finally, the skill processes your request and converts the response back to speech. Amazon was incredibly clever about scaling this system through the Alexa Skills Kit, essentially an app store for voice interactions. Third-party developers could create skills for ordering pizza, booking ride shares, controlling smart home devices. By 2018, there were over 100,000 Alexa skills available. But here's the crucial limitation. Each skill was essentially an isolated system. Alexa couldn't maintain context across different skills or have truly fluid, multi-domain conversations. You couldn't say, "Play some jazz music and also add milk to my shopping list," and "What's traffic like to downtown?" in one natural request. Each intent required a separate, structured interaction.
Now, let's examine why these approaches, both enterprise chatbots and voice assistants, were fundamentally limited. Understanding these limitations is crucial because they explain why the eventual breakthrough came from such an unexpected direction. The first major limitation was brittleness. Rule-based systems could only handle the exact scenarios they were programmed for. If a customer deviated even slightly from expected patterns, the system would fail catastrophically. Imagine you're trying to report an internet outage to a chatbot. If you say, "My internet is down," the system might work perfectly. But if you say, "My Wi-Fi stopped working this morning and now I can't check email," essentially the same issue described differently, the system might respond with, "I don't understand." This led to the infamous "I don't understand" response that became synonymous with bad chatbot experiences. Users learned to game these systems, memorizing specific phrases that would trigger the right responses. It wasn't natural conversation, it was more like learning voice commands for a finicky computer program. The second limitation was scalability. Adding new capabilities to these systems required a massive manual effort. Every new product launch, policy change, or business process update meant weeks of work by conversation designers and programmers. The third fundamental limitation was the lack of contextual understanding. These systems were essentially stateless. They treated each customer message as if it was the first thing ever said in the conversation. They couldn't maintain coherent context across multiple exchanges. Here's a simple example that would break most 2010s chatbots. A customer says, "I need to change my address." The bot responds, "Sure, I can help with that. What's your new address?"
The customer responds, "It's the same as my billing address." The bot has no idea what that means because it doesn't remember that this customer has a billing address on file. These weren't just minor inconveniences. They were fundamental architectural limitations that made truly natural conversation impossible. The commercial world was essentially trying to simulate intelligence through increasingly complex rule systems, but they were building elaborate mechanical calculators when what they needed was a computer. The industry knew about these limitations, but they saw them as acceptable trade-offs. The goal wasn't human-like conversation, it was efficient automation of routine tasks. But this mindset, accepting fundamental limitations as inherent to the problem, is exactly what blinded the commercial world to the breakthrough that was coming from academic research.
While the commercial world was building these elaborate rule-based systems, something completely different was happening in academic research labs. Computer scientists were working on what seemed like an entirely separate problem: how to make computers understand and generate human language at a fundamental level. The story begins with statistical language models, n-gram models that tried to predict the next word by looking at patterns in massive collections of text. These worked for simple tasks, but hit a fundamental wall: the curse of dimensionality. As you tried to capture longer-range dependencies, the number of possible combinations exploded exponentially. The breakthrough came in 2003 with neural language models that represented words as vectors, points in a high-dimensional mathematical space. This is where word embeddings come from. Words with similar meanings would be close together in this mathematical space. King and queen might be near each other, as would walk and run. This solved the curse of dimensionality problem cleverly. Instead of trying to memorize every possible word combination, the model could generalize based on mathematical relationships between word vectors. But these models still struggled with long-range dependencies. A word at the beginning of a paragraph couldn't easily influence predictions at the end. The next major breakthrough came with recurrent neural networks, or RNNs. These were specifically designed to handle sequential data, like language. Unlike traditional neural networks, RNNs had a memory. They could remember information from earlier in a sequence and use it to influence later predictions. Think of an RNN like a person reading a sentence, word by word, but with perfect memory. This was a huge improvement for language tasks. An RNN could learn grammatical relationships between words separated by other words. But RNNs had their own problem: the vanishing gradient problem. As sequences got longer, the influence of early words would fade away. This led to long short-term memory networks, or LSTMs, which had sophisticated memory systems for deciding what information to remember, forget, and pay attention to. By 2010, LSTMs were achieving impressive results. They could generate coherent text, translate between languages, and answer simple questions. But there was still a fundamental bottleneck: sequential processing. LSTMs had to process text one word at a time, from left to right. You couldn't parallelize the processing, making training incredibly slow. Academic researchers knew they needed something different: a way for models to look at entire sequences simultaneously and compare words regardless of their position. This was the research frontier in 2016: how to break free from sequential processing. The commercial world was completely unaware this problem was being worked on, let alone about to be solved.
Then, in June 2017, everything changed. A team of Google researchers published a paper with the audacious title, "Attention is All You Need." This wasn't just another incremental improvement, it was a complete reimagining of how machines should process language. Instead of processing text word by word in order, the transformer architecture could look at all words in a sequence simultaneously and decide which ones were most important for understanding any given word. Let me explain this with an analogy. Imagine you're at a cocktail party, trying to follow a conversation. The old approach was like having to listen to every word in strict chronological order, building up your understanding sentence by sentence. The transformer approach is like being able to instantly replay and cross-reference any part of the conversation. If someone says he, you can immediately scan back through the entire conversation to figure out who he refers to. This is accomplished through the self-attention mechanism. For every word in a sequence, the model creates 3 vectors: a query vector, a key vector, and a value vector. When processing any given word, the model compares that word's query with the keys of every other word in the sequence, telling it how much attention to pay to each word. For example, when processing bank in "I went to the bank to deposit money," the attention mechanism would discover that bank should pay attention to deposit and money, disambiguating that we're talking about a financial institution, not a riverbank. The crucial breakthrough? This attention calculation can be done in parallel for all words simultaneously. Unlike RNNs, transformers can calculate attention for all words at once using matrix multiplication, an operation modern GPUs are incredibly efficient at. This solved both computational and conceptual problems. Training could be massively parallelized, and the model could capture arbitrarily complex relationships between any words in a sequence regardless of distance. Most importantly, transformers could scale. They got better and better as researchers added more parameters and training data. The next few years after the transformer paper were like watching a dam burst. Academic researchers realized they had found something extraordinary, and the pace of innovation accelerated exponentially. In 2018, Google released BERT, bidirectional encoder representations from transformers. Unlike previous models that could only look backward in a sequence, BERT could look both ways simultaneously. It could understand complex pronoun references that would stump most previous systems. Then came GPT, the generative pre-trained transformer from OpenAI. While BERT was designed to understand text, GPT was designed to generate it. By training on massive amounts of internet text, GPT learned not just grammar and vocabulary, but knowledge, reasoning patterns, and even creativity. But here's the crucial point. Throughout this entire academic revolution, the commercial conversation AI world remained completely oblivious. While researchers were achieving breakthrough after breakthrough, companies were still hiring armies of conversation designers to manually program decision trees. Why this disconnect? Several reasons. Academic researchers and commercial AI teams were living in completely separate ecosystems. The early transformer models required enormous computational resources, and the metrics were different. Academic researchers focused on general language understanding, while commercial teams focused on automation rates for specific, narrow tasks. The commercial world was perfecting increasingly sophisticated ways to avoid real conversation, while academic researchers were creating systems that could actually converse. The collision between these two worlds was inevitable. It just took a while for the commercial world to realize what was coming. The moment when these two worlds finally collided was November 30, 2022. That's when OpenAI released ChatGPT to the public, and suddenly everyone could see what academic researchers had been building toward. But to understand the shock this created, you need to realize what ChatGPT actually was. It was essentially a direct application of all those academic breakthroughs we just discussed. There was no gradual evolution from 2010's chatbots. ChatGPT was built on the transformer architecture from that 2017 Attention is All You Need paper, trained using techniques pioneered by BERT and GPT research. The commercial conversational AI industry was completely unprepared for this. Companies that had spent decades perfecting rule-based systems suddenly faced a technology that could handle virtually any conversation topic with remarkable fluency. It was like spending years perfecting horse-drawn carriages and then watching someone drive past in a Tesla. The contrast was stark and immediate. Traditional chatbots would respond to, "I'm feeling sad," with something like, "I understand you're experiencing negative emotions. Would you like me to connect you with our mental health resources?" ChatGPT could have a genuinely empathetic, contextual conversation about feelings, ask follow-up questions, and provide thoughtful advice. Traditional voice assistants required precise commands. "Alexa, set a timer for 10 minutes. ChatGPT could handle, "Hey, I'm cooking pasta and I always forget to check it. Can you help me remember when it might be ready? I think the box said something like 8 to 10 minutes, but I'm not sure." The technology gap was so enormous that it wasn't even a competition. Within months, companies that had spent millions developing traditional chatbots were scrambling to integrate GPT-based systems. The entire enterprise conversational AI industry had to be rebuilt from scratch. But here's what's most fascinating about this story. The breakthrough didn't come from improving old approaches. No amount of optimization could have turned a rule-based decision tree into ChatGPT. The innovation came from an entirely different conceptual foundation.
The idea that machines could learn to understand language by finding patterns in massive amounts of text rather than by being manually programmed with conversation rules. This is a perfect example of what innovation theorists call disruptive technology. The new approach didn't just make existing solutions better, it made them completely obsolete by solving the problem in a fundamentally different way. It's like how digital cameras didn't make film better, they made film irrelevant.
So, what can we learn from this extraordinary story? I think there are several profound lessons here about how innovation actually works in the modern world. First, the most transformative breakthroughs often come from unexpected directions. The commercial conversational AI industry was focused on incremental improvements, better decision trees, more sophisticated keyword matching, more elegant conversation flows. Meanwhile, the real revolution was happening in academic research labs working on what seemed like completely different problems. This is a pattern we see repeatedly in technology history. The inventors of the transistor weren't trying to improve vacuum tubes, they were exploring solid-state physics. The creators of the internet weren't trying to make telephone networks better. Second, this story reveals the danger of premature optimization. The enterprise chatbot industry spent over a decade perfecting systems that were fundamentally limited. They became incredibly sophisticated at managing the constraints of rule-based approaches, but never questioned whether those constraints were necessary. Third, different metrics and incentives can blind entire industries to revolutionary possibilities. Commercial teams measured success by automation rates and cost savings. Academic researchers measured success by language understanding capabilities. Finally, this story demonstrates the incredible power of fundamental research. Every breakthrough we discussed, word embeddings, neural networks, attention mechanisms, seemed abstract and impractical when first developed. But these abstract concepts ultimately revolutionized one of the largest software industries in the world. The lesson is this: in a world of accelerating technological change, the biggest risk isn't that your competitors will do what you do, but better, it's that someone will make what you do completely irrelevant by solving the underlying problem in a fundamentally different way. The conversational AI revolution wasn't evolution, it was revolution.
And revolutions come from outside the existing system. Sometimes the most important question isn't how can we improve what we're doing, but what if everything we're doing is unnecessary? And that's the remarkable story of how conversational AI really happened. The key insight here is that the biggest breakthroughs don't come from perfecting existing approaches. They come from fundamentally reimagining the problem. While an entire industry was building increasingly sophisticated rule-based systems, academic researchers were developing something completely different that would make all of that work obsolete overnight. Thanks for joining me on Mindcast today. If this episode opened your eyes to how innovation really works, I'd love it if you could subscribe, rate, and review the show. It helps more curious minds discover these stories. You can find all our episodes on Spotify or wherever you listen to podcasts. Until next time, keep questioning what you think you know about how breakthroughs happen. This is Will, signing off from Mindcast.